So welcome back class, and this is lecture first, and in this we are going to start the topic thermodynamic and kinetic aspect of metal complex. So this is the actually title of unit thermodynamic and kinetic aspect of metal complex. So in this connection we'll first discuss the types of stability. Okay, what are the different types of stabilities occur in a complex. So types of stability in metal complex. See, as you can see that the title of the unit is what thermodynamic and kinetic aspects. So the type of stability is also belongs to these thermodynamics and kinetic aspects. So there are basically two types. We can distinguish the stability of complex in two type. One is the thermodynamic stability, and the other one is the kinetic stability. Okay, so the first one is the thermodynamic stability. See, the thermodynamic stability consists of bond energy and some stability constant, redox potential. So this thermodynamic stability, it deals with uh, bond energy, then the stability constant, and the third one is redox potential. Okay, so this is the main properties as far as the thermodynamic stability is concerned. So this all things affect the equilibrium conditions. So on the basis of these properties and the thermodynamic, we can divide thermodynamic stability in two types. One is called stable complex, and other one is called unstable complex. Okay, so thermodynamic stability can further classify, can further divide in two types. One is stable complex. Stable complex is also known as penetration complex. Okay, this is also called penetration complex. So what do you mean by stable complex? See, stable complex, as the name itself reflect, that it has a sufficient stability to retain identity in solution. Okay, stable complexes are those complexes which possess sufficient stability sufficient stability to retain their identity in solution. Okay, so this is what the stable complex. Okay, and what about the unstable complex? So second one is the unstable complex. Unstable complex is also known as normal. This is called normal. So just reverse of this stable complex, that means those which are reversibly dissociate in a solution. Okay, those which are reversibly dissociate in solution. Into their components. So this is what the two types of complex as far as the thermodynamic stability is concerned. Now the next type of stability is called kinetic stability. Okay, so second type of stability is kinetic stability. And kinetic stability, what it deals, so it deals with first we all aware about that the rate of reaction. Okay, so the rates of reaction, this is called reactivity also. Then the formation of intermediate complex, formation of intermediate complex, then the activation energy, for the process. So this is what the different categories in kinetic stability of the complex. So again, uh, based on this point, again we can divide kinetic stability in two types. The first type is called Libel complex. Okay, now what is the Libel complex? So such kind of complex in which ligand can be exchanged, where the replacement of ligand is possible, that are called Libel complex. Somewhere it is written as uh, non-inert or active complex also. So Libel complex are those whose one or more ligands can be replaced. Okay, with the other ligands, whose one or more ligands can be replaced replaced by replaced by uh, other ligands. Okay, so this is what the Libel complex. Now the second one is the other, which is called the inert complex. Okay, Libel complex are those which ligands can be replaced by other ligands. The second one is called inert complex. Okay, this is what inert complex, and as the name says, again name says that it is a typical inert complex. That means in which ligands cannot be replaced, or if it is replaced, it replaced by very difficulty. Okay, so whose one, the complex whose one or more ligands cannot be can either not be replaced or can be replaced with difficulty. With difficulty by other ligand. Okay, so this is what the difference of these two ligands. Got it? Now moving ahead, this is the first page. See, stability of a complex, when we are talking about the association or dissociation of a complex, that means formation and dissociation of the complex. So generally we are talking about the stability of a complex ion in solution. Okay, because when you are saying it will associate or it will dissociate, that means we are talking about the complex ion in solution. So stability of complex ion in solution. See, stronger is the metal ligand bond in the complex ion, lesser will be its dissociation. This is very simple concept. If there is a strong relationship between a metal and a ligand, of course it will be not easily dissociate, and so as the stability is will be greater. So this is what the stability of complex in solution. So what we can say that the stronger is the metal ligand bond, metal ligand bond, lesser is the dissociation. Lesser is the dissociation of the complex. And if the lesser dissociation, then greater is the stability, and hence greater is the stability. So this is what the role of a complex when it is in solution form. So we can define this as a measure of resistance of the replacement of ligand by another ligand. Okay, this is the measure of because once it is in solution form, once a complex is in a solution form, if it is able to replace that ligand, then it is a Libel complex. So that is what the dissociation of complex definition says. So we can say that the it is a measure of, I am writing here, it is a measure of the resistance of the replacement of a ligand by another ligand. Replacement of a ligand by another ligand. Okay, now we'll discuss the expression, the mathematical expression. What would be the mathematical expression in order to find out the value? So dissociation of a complex ion solution, that means the dissociation constant we are talking. So dissociation of complex ion in solution. So what we are talking about? We are talking about the dissociation constant. Dissociation. Okay, dissociation can be written as instability. Dissociation is what? Instability. Because if it is stable, it will not dissociate, and if it is unstable, it will dissociate. So dissociation is some sort of instability. Dissociation constant, and dissociation constant can be represented by K dissociation. Short you can write DISS or KI. KI is what? Instability constant. So dissociation constant can be represented by this. Okay. So what will happen actually when a complex is dissociate? When a complex is dissociate, there is lies an equilibrium between the undissociated complex ion and the species which is obtained after dissociation. Okay, so when a complex ion dissociates, there lies an equilibrium. Okay, there lies an equilibrium between what? Between complex when a complex ion dissociate, there lies an equilibrium between the undissociated complex ion and species obtained by the dissociation of the complex ion, by the dissociation of the complex ion. So now we'll take the example of this statement. So let's take an example. See, we have an example of dissociation of copper complex. Okay, so we'll discuss the dissociation of copper complex ion. CuNH3 whole 4. This is the complex of copper ion. Okay, so how it will be how after dissociation the equilibrium will be established. So CuNH3 whole 4 2 plus, it is a equilibrium, so this is the sign of equilibrium, and this will dissociate into copper 2 plus and 4 ammonia. Okay, so what it will be the dissociation constant? So the dissociation constant is something which is called instability constant also. Okay, so dissociation constant, that means K d I double S, and that is equals to what? Product upon reactant. Okay, so the product will be what? Copper plus 2, then ammonia, this will be 4, and this is the power actually. Okay, and in product reactant side, CuNH3 whole 4 2 plus. Okay, so this is the equation of dissociation. This we can written as equation number 1. Okay, now this is the dissociation constant. Okay, let's talk about the formation of a complex. This is the dissociation of a complex. So what it will be the formation? So the formation of a complex is called formation constant. So formation constant, formation. So if it is instability, dissociation is instability. So formation is what? Formation will be stability. So formation, or we can say that stability. Okay, formation constant. So formation constant can be written as what? K FOR. This FOR indicate that formation, or stability. So we can write it Ks, but the notation is beta actually. For formation constant, the notation which is used is called beta. Okay, so you have to very particular about this. This is not, this you cannot written as Ks, like this is Ki. This is not Ks, it is a beta. Okay, so let's take an example of this. Again, we'll take the same example. Okay, because the if this molecule is formed, that means if this form, so how it will form? It will form by the what? Copper and ammonia. So again the example will be same, copper plus 2 and 4 ammonia. This will give you CuNH3 whole 4 and copper 2 plus. Okay, so this is what the formation of a complex ion. Now we will write the stability constant here. So stability constant, or formation constant, you can write also formation constant. This we can represent by K4 or beta. So you can write it beta, more better to write it beta. Again, product upon reactant, so product is what? copper NH3 whole 4 2 plus, and at the reactant side copper 2 plus and NH3 4. So this is nothing but equation number second. Got it? So from equation number 2, from equation number 1 and 2, as you can see that the equation number first and the equation number 7 are just opposite to each other. Okay, they are reverse of each other. So what we can say that the K for or beta, that is equals to 1 upon K dissociation or Ki. Okay, so this is the relationship between formation and dissociation, and it has great great numerical data, so that we can explain it further about the stability of the complex. We'll take some example. So this is what the difference I have written, that there is a relationship between the formation constant and dissociation constant. Formation constant is just reciprocal of dissociation constant. So we'll take some example on the basis of this data. So let's move for the next page. See, we'll take some example. Of course the experimental values will take. So here I'm just writing the complex ion. Here is the K dissociation, and here is the K formation. So as I told you, it will be just opposite to each other. So let's take an example of copper first. So the value for dissociation for this complex is 1.0 10 to the power minus 12. So if it is opposite of this, what will it will be 1.0 into 10 to the power minus 12, sorry, plus 12. This will be plus 12. Okay, because this has inverse relationship. One more example, cobalt complex. So in this case the value is 6.2 10 to the power minus 36. So what will be the value in formation constant? 1 upon this. So while dividing by 1, this will be 1.6, and this will be 10 to the power 36 positive. Okay, similarly let's take one more example, silver complex, thio complex. This is S2O3 whole twice 3 negative. Okay, so value here is 6.1 10 to the power minus 14, and here is 1.6 into 10 to the power plus 14. So this is how you can explain the formation and dissociation constant value. Got it? HgCN whole 4 2 negative. So this is 4.0 10 to the power minus 42, and this will be 2.5 10 to the power 42. Okay, plus similarly this is the last. I'm putting this just for the explanation. You can is very easily explain on the basis of this values. So this will be 1.0 10 to the power plus 3. Now what information we can collect from this data? See, we all know that there is a relationship of what beta is inversely proportional to what Ki. Okay, so what it reflect? It reflect that the we can say that the maximum value for this beta is what formation constant. So the maximum value is this one, HgCN4. Okay, so this will be the most stable complex because it has formation constant is maximum. Okay, formation constant is inversely proportional to dissociation constant. So HgCN4 2 negative is the most stable complex. Got it? And this you can see that it is minus 3 value. Okay, so this FeSCN plus 2 is the least stable because it has a least value of formation constant. Okay, so FeSCN 2 plus is the least stable ion. So this is how you can predict the stability of a complex on the basis of the formation and dissociation constant. Okay, so this is what the introductory lecture of the first the second unit of the syllabus. Okay, and I hope you enjoyed this. Thank you so much for your watching.